Okay, so let's quickly go over how to make those graphs and run the stats. So the first thing that you need to do is load the tidyverse library, and that has all of the packages that we need to use. And then we are already in the right working directory, the folder that has our files in it. And so we can read our data into R to load it. So I'm going to call this histdata and use the command read CSV, which can autocomplete if I don't type the whole thing, and tell it to read the file called tissue measures.csv. So I'm just typing tissue tab to autocomplete and choosing the file that I want. And if I press Control Enter, that runs. And we can click on this to look at the file that we've just loaded. And that looks right. So we'll go back to our script. And this has all of the intestinal measures in it, but we don't have any of the metadata, like which diet the mice were on. So I'm going to load that file and call it sacdat for the data that we collected at collection. And again, say read CSV and load that CSV. And then we need to, if we look at our histdata, the mouse ID column doesn't actually just have the mouse ID. It has the ID and the section, so colon or ileum, and which section that was from, and .tif. So I want to just get this first bit out of that column. So to do that, I can take histdata and either use the bidirectional pipe or just assign histdata to that again, and then use a singular directional pipe and say separate, and the column we want to separate column equals mouse ID, because that has the mouse ID in it. And we want this to be separated into, and then we use a C to indicate we're separating into multiple different columns. And we'll call the columns, we'll give them the titles mouse ID, or the names mouse ID, drop, because we don't want the next bit, and drop 2, because we don't want the next bit. So it doesn't matter what we call them. And then the character that we are using to separate it, if we look at histdata again, we can see that there is an underscore between those sections. So we just tell it separate using the underscore character, so it knows what to look for. And then if we run that, it'll have 3 columns, but we don't want drop 1 or dropped 2. So we can select and say minus to say not. We don't want drop, and we don't want drop 2. So if I run this and look at histdata again, now we have this mouse ID column that has just the mouse ID, and the other 2 columns, drop and drop 2, are no longer there because we selected to remove them. Okay, so now we have a data frame with the mouse ID. We want this to be in a long format. So right now we have the 5 different villi or crypts that are in different columns, but we want them to instead be a different row for each of these so that we can work with the data more easily. So we're going to put this into a long format, call it histdata again, and use the command pivot longer, which will take data from a wide format and put it in a long format. So the columns we want to pivot on, if we look at this data frame again, 1, 2, 3, 4, 5, they all start with a lowercase x. So we can use the command starts with x, and then it'll take those 5 columns, because they're the only ones that start with x, and we want the names of those columns to go to a new column called rep, for which replicate it is. And the values to, we want a new column called value, where all of the numbers in those columns are going to go. And then values drop NA. If there's any missing value, any NA, we want it to drop that instead of making a new row for it. So, and then the columns that we want to select to make our data frame a little tidier are, we need the mouse ID, we need the tissue, we need the area, measure, and then those two new columns, rep and value. So if I run this now and we look at hist data, we can see that for control 49D, for example, for colon crypt depth, the replicates are now 1, 2, 3, 4, 5 in different rows, and the values are in the new value column. Okay, so now that we have them in the long format, we can get the average of those 5 replicates for each of the measures we're interested in. So I'm going to create a new data frame called hist sum for summary, and take our hist data frame, and I'm just going to specify we're using the package dplyr, and the command is group by, because we want to summarize within each mouse ID. We don't want to average across all mice, and also within each tissue, so whether it's colon or ileum, within each area, whether it's villus or crypt, and for each measure, whether it's length or goblet cell count or whatever, because we wouldn't want to average or find the average of goblet cell counts and villus length for one value. That wouldn't make sense. So that's what we're grouping by. Then pipe that again into dplyr, and the command is summarize. This is going to give us a new column. We'll call it mean, and we want this column to contain the mean of value. So if we run this, we can see the new object, hist sum, appears in our environment. If we click on that, we can open it and look and see now, for example, for mouse C33B, for ileum crypt depth, we only have one measure, and that's the mean value of those 5 measures from before. And then for ileum crypt goblet cells, again, it's also taken the mean value. So for each of these group by variables, it's made one mean value for each combination of those group by variables. Okay. So now that we have the mean value, we can put this back into a wide format. So I'm going to create a new data frame again and call it summary data or sum data, and assign to this, take the hist sum data frame and pipe that into, using the tidyr package, the command pivot wider to make this a wide data format. The new column names for the new columns we're creating when we're making a wider data frame will say names from, so it knows where to take the names from. And we'll say we want it to take the names from all 3 of tissue, area, and measure. And we want the values to come from mean, because that's the column that has our data in it. And we want the names to be separated by a space. So if we run this, we have a new data frame, sum data. When we look at this, we can see now we have a row for each mouse, control 33B, and each different measure is in a different column. So we have ileum crypt depth, ileum crypt goblet cells, ileum villus goblet cells, etc. So there are some measures that we want to analyze that weren't directly measured in our data, and we can run those calculations in R as well. So taking our sum data frame and assigning it back to itself, we can use the command mutate, which is used for many different reasons, but here we're using it to create some new columns and create a column called ileum villus density, which is going to be equal to ileum villus goblet cell divided by ileum villus length. And I'm putting each of these column names in backticks so that even though there are spaces between the different words, it interprets this as one thing because these aren't supposed to be in quotes. So that's what the backticks are for. And we'll do this for a few other measures. So we'll also have ileum crypt density, which is going to be ileum crypt goblet cells divided by ileum crypt depth. And we'll do colon crypt density, which is equal to colon crypt goblet cell divided by colon crypt depth. And then finally, we want the ileum villus to crypt ratio, which is equal to the ileum villus length divided by ileum crypt depth. Okay, so when we run this and open some data again, we have these new columns for the variables that we just created. So this data frame still doesn't have any information about diet or age or sex. So we're going to join this with our SAC data frame that has the mouse IDs, as well as maternal diet, age, sex, and a bunch of other data. So to do this, we're going to create a new data frame called hist meta, because it has the metadata, and take our sum data frame and say left join. So there's a few different joins. You can look into this more if you want to, but for now, we'll just go over left join. This is taking that sum data frame and looking at the data frame that we're joining it to, which in this case is SACDAT, seeing what columns have the same name. So both SACDAT and sum data have a mouse ID column, and that's the only one that's the same. So it's going to look at sum data and look for each mouse ID and find that mouse ID in the data frame SAC data and add all of the columns for that mouse to this new data frame. So when we run this, we have hist meta, and now we have mouse ID, all of the measures we had from our sum data frame. But if we scroll over, we also have all of the measures for that mouse from the SAC data frame. Okay. So final step before we are graphing this and running stats to make this easier is we're again going to pivot this longer. And I know it seems like we're pivoting longer, wider, longer. It's going back and forth, but that's just because in certain formats, it's easier to do certain things to the data. So it's easier to switch it back and forth and take the mean or add it to the SAC data frame than do it another way. So to put it longer, again, we're going to say hist meta and take that hist meta data frame again and the command pivot longer. The columns that we're going to pivot longer are all of our measures columns. So I'm just going to copy paste this because it's quite a lot of typing. Oh, let's see. The spacing is a little weird because I'm so zoomed in. I'm just going to make it a little cleaner. Okay, so those are all of our columns. I'm just going to clean this up a little so it's easier to see. Oh, backtick. Okay, so there are all our column names that we want to pivot longer. And we're going to say names 2, and the new column name that we're going to make is measure values 2, a new column called value, and again, values drop NA equals true. And then we are going to drop NA value age. So this means that any row that has an NA in the value column, so any row that doesn't have an actual data point for the value, or any row that has an NA for age, we're going to drop. So now if we look at HistMeta, we have that metadata still from the SAC data frame. And then if we scroll over, we can see all of the different measures are now a different row, and the values that correspond to them are in the value column. So the final thing, actually, we probably don't need to do this part, so I'll skip that for now. Okay, so now I'm going to make these measures a little bit easier to work with. Right now, they are one column that tells you if it's ileum villus length or ileum villus goblet cells or whatever it might be. It might be easier if those are in 3 separate columns. So I'm going to make a new data frame, histmeta2, and take histmeta and pipe that into the command separate again that we used before. Take the column measure and separate it into 3 columns called section, area, and measure, and use the separator equal to a space and say if there's any extra columns, if there's more spaces than we've made columns for, merge them together. So when we run this and look at our new object histmeta2, we can see that we now have 3 different columns, section, area, and measure that tell us ileum, cryptor, villus, whatever. And because we said merge, even though there's a space in goblet cell, it's put these into measure instead of dropping cell, which it would have done otherwise. Okay, so I think now we are ready to make a plot. We are going to use this data frame that we just made and assign this to the object P for plot. So I'm going to, first off, the easiest way to make the plot is to select which things from our data frame we want first. So I'm going to make a new data frame called dat and take this data frame we just made, histmeta2, and say filter. So this is going to filter for the rows where section is equal to ileum, just as a first off, and area is equal to villus, and run that. Oop, did not like that for some reason. It's because I called it wrong. Histmeta2, not histdata2. Run that, and now we have dat. So it's just a subset of the histmeta2 data frame where all of the sections are ileum and all of the areas are villus. And then we can make our plot, taking this dat data frame, piping it into ggplot, and assigning the aesthetic mapping. So on the x-axis, we can put age. I need a comma. On the y-axis, we can put value, and we can color the plot by, not in quotes, maternal diet. And then to this plot, we can add the geome point. And if we just run that, it creates a new object P, where if we then call on P, it'll put out the plot. So this is not a super informative plot right now because it's just value on the y-axis. Because if we look at at DAT, this value column has a bunch of different measures. So to separate these out on the same plot, we can say facet grid to make different plots and facet it by measure. And I need to have a little squiggly. Facet it by measure. So now we have 3 different plots, which makes more sense, where we have density separate from goblet cells, separate from length, but it's still not a very informative graph. And we also have males and females in here, so we want to look at both of them. So I'm going to say measure by sex for facet grid. Now if we call on this, we have females on the left, males on the right, and different rows of graphs for the different measures. It's still not great because all of these y-axes are the same. So you can't actually see the data for the lower values because of how high the value for length is. So to make different y-axes on these different plots, we can set the scale equal to free y for the y-axis. And I'm also going to switch y. And now if we call on this, the different names are on the left instead of on the right, and there's axes that are appropriate for each of these values. So this is a better graph, but we can still improve it from here. I'm just going to minimize this so you can see. So some things that we can do are be a little more specific about how we want these points shown, because right now they are overlapping. So we can say for the position of the points, we want to set position of jitter dodge so that the points are not all in a straight line up and down, and say jitter width equals 0.4. You can play around and see what the right jitter width is. Dodge width equals 0.5. And I'm just going to put that on a new line. Also, we can apply some aesthetic mapping here. So we want them to be dodged by a group of maternal diet, and color equals maternal diet. So now if we run this and call on the P object, that jitter width is probably too much in this case because they're overlapping, but you can see that the control and high fat are separated out to the sides for each of the ages that we have. So I'm going to change the jitter width maybe to 2.2 and see how that looks. That's a bit better. Anything else we should do with that? I think that's good for now. So we can also change the colors by adding scale, color, manual, and setting the values equal to black and red. And we can add, this is just showing all the points. You could add a box plot. I like to add a point for the mean and show the standard deviation. So you can do this adding stat summary and then tell it the function of the data that you want it to use is the mean SD, mean and standard deviation, and then position this so that it lines up with your points. You can say position equals position dodge, width equals 0.5. And then we need to apply that same aesthetic mapping as well as the points. AS group equals maternal diet, color equals maternal diet. Oh, I forgot to add a plus after this. So we can say plus, so it runs everything together, P. And now we have these points. It did not dodge properly though. That's because position isn't spelled right. Position. And now it's dodging properly. And then for the geom points, because it's a little bit hard to distinguish the points from the mean and standard deviation, and we maybe want the mean and standard deviation to be a bit more obvious, we can set the alpha, which is the transparency, to 0.3. And now it's easy to tell apart the individual points from the mean value, and also to see all of the individual points and the mean value. Okay, so we can add a few more things to make this plot look as nice as possible. And we can do that using theme. So plus theme, I'm gonna add another plus at the end here. The strip background is that gray box around the faceted strips. We can say element blank to remove that gray box. It's kind of ugly. And we can, let's just run that first. So that looks a little bit nicer. Okay, so for the stats, we want to do a similar thing to what we did with the plots, but here we have all the different measures in our DAT data frame, and when we're running stats, we want only one of those measures because we want to run stats differently for each measure. So we can take, we can make a new data frame again, DAT. It's okay that it overwrites it as long as you run everything in the right order, or you could call it something different. Hist meta 2, and again, filter. So we can say now we want it to filter same as before. Section equals ilium, area equals villus. I'm going to put these each on a different line. And now we want to choose one of the measures. So we could say measure equals length to select just this bottom plot here, that data, and run this. And that didn't work because this should be 2 equal signs, not 1. 2 equal signs means equal to. 1 equal sign is an assignment. So it's setting that as equal to, not checking if it's equal to. So run that now. And now we have the DAT data frame that only has ilium villus length for every single row, and then the values for all of those. So we can use that data frame to run our stats, and we're going to create an object that's the output of a linear model and use the command lm, which is for a linear model. And this is very similar to a t-test or an ANOVA, looking for statistical differences in our outcome variable, which in this case is called value. And we're going to test for whether value varies by the independent variables we are interested in. So in this case, that is maternal diet and sex. So I'm going to use an asterisk because there could be interacting effects of maternal diet and sex. And this is equivalent to a two-way ANOVA where the two factors are maternal diet and sex. And we'll tell it to use the data from DAT. So if we run this, nothing comes out because we just created a new object, but we can say ANOVA LM to give the results here, where it will print out the p-values. And if we wanted to test, in this case, nothing is significant, so we wouldn't test for, do any post hoc tests for multiple comparisons, but if we were going to do multiple comparisons, we use the command emeans and say, take this model we made, LM, and look, we can do pairwise by maternal diet within each sex. And if we put, then it'll tell you for the females if there's an effect of maternal diet, and for the males what the effect of maternal diet is, and what the p-values are for those. And you could also put this to an output called EM, and then say pairs EM, and that will output the p-values for those comparisons. So there's no statistical difference here by maternal diet for overall, but we are also still looking at all of the ages. If we look at DAT, we have both P14 and post-high fat diet. So we actually want to look within the ages. So I'm going to say filter again to make a new data frame. Let's run it on P14 first. And now if we run this, we can create LM, run the ANOVA on LM. So for P14s, there is no significant effect of maternal diet, of sex, or of an interaction between maternal diet and sex, which makes sense because the data don't look like there's anything significant. And if we run the e-means and look at the pairs, again, nothing significant. And then you could do the same thing. So just copy paste this. Maybe make it a new block in R so that you can keep them separate and say post-high fat diet instead. And if we run this, we can see for post-high fat diet, again, there's nothing significant. And for the e-means, there's nothing significant. So we know, which makes sense looking at this data. It doesn't look like there would be. But then you can change out for each of these measures to cover everything. And there is an easier way to do this automatically, but it's a bit more complicated. So we'll cover that later. But for now, I think that it's fastest to go through it this way versus trying to figure out the automated way to do it. So we could also look and see if there is something that we expect there to be a difference for. It doesn't really look like any of these are super different, but maybe if we look at, what did you say was different? Ileum crypt, goblet cell density. So if we say, instead of ileum villus, ileum crypt, and run this, goblet cell density, significantly different. Sure, let's run the stats for that. So if we look at P14, ileum, switch out crypt, density, run that to make DAT. Doesn't look significantly different for the P14s. Yeah, nothing in the P14s. Let's look at post high fat diet. Nothing there either. So I think that there might be too few points for that. Maybe you'd been running it all together. Yeah, so if we run them together, that's almost significant. But if we were running them together, we would have to also include age as a factor here. So now we have all of these interactions, and there's still almost a significant effect of age within sex. And let's say, is that the right syntax? Plus age? Yeah, so P14, nothing, 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 nothing significant. But I think that's because the sample size is pretty limited.